Hi and welcome to part 2 of Module 3. In this part we look at diversification and we introduce the modern portfolio theory. The learning objective for this part is firstly to explain how diversification reduces risk, and this relates to the way that we calculate portfolio variance from the previous from part 1 of Module 3. We then explain the concept of the efficient frontier, or the foundation of modern portfolio theory. The efficient frontier is computed based on the idea of diversification. We then look to explain the importance of covariance between returns on risky assets in determining the risk of a portfolio. So once again, this relates back to the way we calculate portfolio variances. We then explain the distinction between systematic risk and unsystematic risk, and why systematic risk is important to investors. The lecture contains 3 parts. In the first part, we look at diversification. We introduce the concept of diversification, or combining different assets in a portfolio so that we can reduce the total risk of the portfolio. Stemming from diversification, we then have systematic risk and unsystematic risk. So in part 2, we introduce the concepts of systematic risk, unsystematic risk, and how they are related. Finally, in the third part, we introduce modern portfolio theory. So diversification focuses on how, when we combine different assets, the correlation or the covariance between different assets can help reduce the total risk of the portfolio. Right. So this relates to the previous topic, where we look at how to calculate portfolio returns and risk. Yeah. So with portfolio risk, recall that we have 2 components in the calculation. The first component being the sum of all the individual asset variances, and the second component being the sum of the correlations, right, or the covariances between the assets. So if we have assets that are less than perfectly correlated, or the rho is less than 1, then the total portfolio risk, or the total portfolio variance, would be reduced, right? So to illustrate, let's look at a few cases where we have assets of different correlations. Yeah. So in the first case here, we have an extreme case where the assets have equal returns and equal risk, but the correlation is a perfect negative correlation, right? So -1. So with the rho of -1, this means that when one asset goes up, when one asset returns goes up, the other asset return go down by the same amount, right? So if we were to illustrate the return and risk relationship of these 2 individual assets and a equally weighted portfolio, combining these 2 assets, this is what we have. So as you can see, this is the return patterns of asset A. So sometimes asset A goes up, sometimes it goes down. Likewise, asset B's returns varies as well. But when asset A moves up by, say, 10%, asset B moves down by 10%, right? So if we combine these 2 assets in an equally weighted portfolio, then an increase in the return of asset A would be offset perfectly by a decrease in the return of asset B. So that in total, we will see that the variability of the portfolio combining these 2 assets would be 0, right? So this portfolio's returns do not vary at all. So in the case where we have a -1 rho, or the -1 correlation coefficient between these 2 assets, we will have a portfolio risk of 0, right? So besides a rho of -1, we have we might have different correlation coefficients, and in the next few slides we're going to illustrate how the correlations between different assets can reduce the total risk of the portfolio. So consider a more generalized example. Let's say we have two assets, asset A and asset B. These are the returns, the expected returns of these two assets. And here we have the standard deviations of the two assets. Yeah. Consider also that we can construct, we have different ways to construct a portfolio. So we can vary the weights that we give to each asset, right? So suppose that we are considering these five different portfolios with different weightings for asset A and asset B. So with portfolio 1, we put 100% of our money in asset A. So the weight for asset A is 100%, whereas the weight for asset B is only 0, right? For portfolio 2, we once again have the same two assets, A and B, but now we put 2/3 of our money in asset A and 1/3 in asset B, yeah? And so on and so forth. So based on the weights of the different assets and the expected returns and risks of these two assets, we can then calculate the portfolio expected returns and risk. Yeah? So recalling from last week, to calculate the portfolio returns, the portfolio expected return is simply just the weighted average of the individual asset returns. So in this case, we have two assets, and therefore our portfolio expected returns is simply just the weighted average of these two assets. So we're given the weight and we're given the expected returns for individual assets, and therefore we can work out the expected returns of the portfolio of each of the 5 portfolios that we saw in the previous slide easily. For the portfolio standard deviation or variance, besides the assets' individual weights, individual returns, and the individual standard deviation, we also need the covariance or the correlation between the two assets, right? So we need this term over here to calculate the portfolio standard deviation. Okay. So this is the formula for the standard deviation of the portfolio of two assets. Yeah. So assuming that we have a positive correlation between the two assets that we saw in the previous slide, so the correlation coefficient here is a perfect positive one, right? Recall also that these are the weights of assets A and B for different portfolios that we are considering. So given the weights and given the expected returns of individual assets, we can calculate the expected returns for each of these portfolios, right? For the portfolio standard deviation, we're given the correlation coefficient. We then therefore can apply the portfolio standard deviation formula to work out the portfolio standard deviation, right? So we now have the portfolio expected returns and the portfolio standard deviations. What we want to see now is we want to see the relationship between risk and returns. Yeah. So what we are going to do next is that we're going to plot the returns of these different portfolios against the portfolio standard deviations. So from the numbers that we calculated before, we can plot the different portfolio risk and return combinations on the graph, right? And it's going to look like this. So we have 5 portfolios ranging from portfolio 1 to portfolio 5. So portfolio 1 has 100% allocation to asset A and 0% allocation to asset B, right? And portfolio 5 has 100% allocation to B and 0% to A. Okay. So with a perfect correlation of +1, we have a linear relationship between risk and return, right? Going from P1 to P5. Now let's look at a different case where we have a less than 1 correlation coefficient. So in the second case, we are looking at once again an extreme case where we have a perfect negative correlation. So rho here is -1. Yeah. So we apply the formula to calculate the expected returns and the standard deviation for each of the 5 portfolios that we considered before. Recall that the portfolio weights remain the same, right, as the previous case. The only difference here is we have a different correlation coefficient. Right. So as you can see, the expected returns for this portfolio stay the same, right? So the returns of the portfolio doesn't depend on the correlation coefficient. It only depends on the weights and the expected returns of individual assets. Yeah. So this stays the same as before. The only difference is the standard deviation of the portfolio. Right. We once again plot the returns against the risk. So expected return on the vertical axis against standard deviation on the horizontal axis. And let's look at how returns and risks change. Yeah. So with a negative 1 correlation coefficient, if we plot the return and risk of different portfolios on the graph, it looks like this. Yeah. So we have the 2 lines starting from P5 to P1. So once again, the weightings for each of the portfolios stay the same as before. The only difference here is we have a different correlation coefficient, and therefore the standard deviation of the portfolio changes. So with P1, we once again have a 100% asset A weighting and a 0% weighting for asset B. So P1 reflects the risk and return of asset A. P5 has 0% weighting to A, but 100% weighting to B. So P5 reflects the risk and return of asset B. Yeah. So looking at the 2 lines, what's the difference here? So if we were to pick some point at this level of risk, so if we were to pick 2 portfolios with 30% of standard deviation, one portfolio lying on this line where the rho is +1, and the other portfolio lie on this line where the rho is -1. We can see that at the same level of risk, this point here, so we just call it X, portfolio X has a higher returns compared to portfolio Y. Yeah. So it shows us that if we have a lower correlation coefficient, we would be able to achieve a higher level of return at the same level of risk, or a lower level of risk at the same level of returns, right? So this is to illustrate the benefit of diversification. Yeah. So when we combine different assets of less than perfect correlations, then the total portfolio risk can be reduced. Right. We then look at the third case where our correlation coefficient is 0. So no correlation at all between the assets. Yeah. So we once again using the weightings of the 2 assets in each of the portfolios and the expected returns of the assets. We can calculate the expected returns of the portfolios, and this is again the same as what we saw before, right? So expected returns don't vary with correlations. Expected standard deviation, this will depend on the correlation. So at the correlation of 0, these are the portfolio standard deviations. Let's look at how this is plotted on the graph. So on the graph, this green line is where the row is -1. This red line is where the row is 1. This blue line here, what we have here now, is when our row is 0, right? So as you can see here, a -1 correlation coefficient is when we have the maximum diversification benefits, right? So this is when risk is minimized. When we have a row of 0, the portfolio curve or the combination of the portfolio lies somewhere in between the red line and the green line. So with a correlation of 0, we still have some diversification benefits compared to the perfect positive 1 correlation case. But it's a bit less than when we have a correlation of -1. Right. So to generalize, on this graph, what we see is that we see different combinations of portfolios at different levels of correlations. So our first observation is the lower the coefficient, the higher the diversification benefits, or the higher the expected returns for any given level of risk. Right. When row is -1, this is when we have 0 risk, right? So no variance in portfolio returns. Point 3. So if we have a risk-averse investor, the investor would never hold any portfolios that lies along these dotted lines, right? This is because they can do better at any level of correlation. They can always find a better portfolio on the solid line, right? So they would never choose any portfolios lying on the dotted lines. So the benefits of combining different assets with less than perfect correlation is what we call diversification benefits, and this is the foundation for modern portfolio theory. So from the previous slides, we illustrated how when we have two assets and at different levels of correlation, we illustrate how the returns, the total risk of the portfolio can be reduced if we have less than perfect correlation, right? So less than perfect 1 correlation. So to generalize, when we have a perfect positive correlation, this is when we have no diversification benefit at all, right? So when we combine different assets, the risk of the portfolio would simply just be the weighted average of the individual asset risk. That's when we have a linear relationship between risk and return, as we saw before. So a portfolio risk is simply just the simple weighted average of individual asset risk. We achieve diversification benefits when we have less than perfect positive correlation, right? And the lower the correlation, the higher the diversification benefits. Okay. When we have negative correlations, we have higher diversification benefits compared to when we have positive correlation. But when we have positive correlation, we still have some diversification benefit as long as the correlation is not positive 1. Right? When we look at the investor's utility, we will see that at the higher level of, at the lower level of correlation, the investor can achieve a higher level of utility. Right. So recalling from the previous week, what we have here on the paper curves are the utility functions. So any point on one utility curve have the same utility. Any combination of risk and returns on the same curve has the same utility. Yep. When we move upward from one curve to the next, this is when the utility increases. Right. So considering three cases of correlations, in the first case we have a -1 correlation. In the second case, the blue line, we have a 0 correlation coefficient, and in the red line we have a +1 correlation coefficient. So as you can see, as the correlation reduces, the tension point between the investor's utility curve and the combination of portfolios moves from this point to this point and finally to this point. Right. So let's compare the utility of these three different points, different portfolios. Right. So at this point, our risk is about 33 or so, and our return is about 15.5, yeah, so somewhere between 14 and 16. So let's call this point x1. At point x2, our risk is a bit less, so this is about 29, right? Our return is around the same as before, so around 15.5. At x3, or at the tension point between this utility curve and the green line, our risk is reduced a bit more, but our return increases a bit more, right? So what we see here is that as the correlation coefficient reduces, we get more efficient portfolios, in the sense that we would have either a lower level risk or a high level returns. Right. So in the previous slides, we illustrated the benefit of diversification for portfolios with two assets. So we look at how different correlations of the two assets affects the total risk of the portfolio. Now let's generalize and look at a case where we have more than two assets, right? So if we were to consider a portfolio with n assets, right, what would happen to the variance-covariance matrix? Yeah. So to calculate a portfolio standard deviation or variance, we need to construct a variance and covariance matrix like what we saw from last week, where, say, if we have three assets, we would have something like this. So weight A, standard deviation A, weight B, standard deviation B, weight C, standard deviation C. Right. We have the same thing here. Weight C, standard deviation C. Right. So if we have a portfolio of three assets, we would have 9 different terms coming from the variance-covariance matrix. Right. If we have an n asset portfolio, the total terms from the matrix would be n squared. Right. So of these terms, we have n variances, which are given by these boxes over here, and the remaining n squared minus n are the covariances terms, right, which are the rest of the matrix, right. From the n square minus n covariance terms, we have n square minus n divided by 2 pairs, because for any of the variance covariance matrix, we will be able to identify identical pairs of covariances. Yeah. So for a portfolio of n assets, we will see that as the number of assets becomes larger, the effect of the covariance terms on the total risk of the portfolio will increase, and it will dominate the effect of the variance terms. Right. So to illustrate, let's consider a simple case where we have equally weighted portfolios. And for these portfolios, we have n assets. Right. We also simplify the case by making each asset's variance the same. So each asset's weight would be 1 divided by n, and each asset's standard deviation would be sigma I. Right. So using this information, we can construct the portfolio variance. Okay. So using the formula to calculate the portfolio variance, we know that there will be n variance terms. So n times yi square times sigma I square. Right. Yi square is 1 divided by n square, given that the weight for each asset is 1 divided by n. Right. The second component of the formula is the covariance terms, right? So we have n square minus 1 covariances. This is the correlation coefficient between individual assets. This is the standard deviation of asset 1 times standard deviation of asset 2, but because we assume that the standard deviation of different assets are identical, therefore we simplify the equation to this term, right? And this is the weight square. Okay. So weight asset A times weight asset B, but because the weights are equal, so we have the weight square here. So we then simplify the equation and reduce it to these terms, right? So looking at this equation over here, this equation implies that when n increases, as n increases, the variance term would reduce, and the only thing that is left is the covariance terms, right? So as n approaches infinity, the variance term would reduce to 0. So when n increases and becomes very large, the total term here reduces and approaches 0. Whereas the covariance term would become this, right? So rho times sigma square, and this is the covariance of returns of different assets in the portfolio. Yeah. So the implication here is for very large portfolios where we have very large n, only the covariance matters. Yeah. So from the generalized case that we looked at before, where we see that for very large asset portfolios, when the number of assets is very large, the effect of the covariances between assets dominates the effect of individual assets standard deviation, right? So what it means is that the individual or asset specific risk becomes less relevant in a large portfolio. Okay? Only the correlations or the relationship or the co-movements between assets within the portfolio would matter in this case. Right? So this therefore leads to the concepts of systematic risk and unsystematic risk. So systematic risk is something that all assets are exposed to, so something that is market-wide, whereas unsystematic risk is idiosyncratic risk, right? So it's something that is specific to a certain company or a certain asset. Okay. So when we express these concepts in terms of the correlation coefficient, so when we think about a correlation coefficient, it shows us how much two assets move together, right? So a correlation of 0.5, for example, shows that 50% of the returns of the two assets could move together, meaning that some variability of the asset returns is due to common factors, and some other factors are asset specific, right? So the common factors that make assets move together is what we can think of as systematic risk. So something that all assets are exposed to, right? Something that makes asset returns move together. For example, industry factors. Say oil prices in airline industry, for example. When oil prices increase, the cost of running airlines would also increase, right? So that's something that is common for all of the airline companies in the industry. Unsystematic risk, however, is variations in returns that is asset specific or company specific, right? So if we have a correlation of 0.7, for example, so 70% of the asset returns could move together, but 30% of the asset returns are due to individual company risk, right? So if we have a large enough portfolio over any given period, the firm-specific effects, the firm-specific factors might be positive for some companies and negative for others. On average, these firm-specific or company-specific factors would therefore cancel each other out. So this implies that for unsystematic risk, if we diversify our portfolio, we might be able to eliminate those risks because different individual risks might cancel each other out. The only thing that we can't diversify away is the systematic risk, right? Because all companies are exposed to the same sorts of risk. So we can't really eliminate by diversifying our portfolio. So to show the relationship between systematic risk and unsystematic risk on the graph, this is what we have. So on this graph here, we have on the vertical axis the standard deviation of portfolio return, or the total risk of the portfolio. On the horizontal axis, we have the number of securities, right, or the degree of diversification in our portfolio. The downward sloping curve here shows us that when we have more securities in our portfolio, the total risk of the portfolio would reduce, and the source of reduction is from the unsystematic risk component, right? The systematic risk of this portfolio doesn't change, right? If we hold assets that are exposed to the same common factors, say if we hold Australian assets, we would be exposed to the risk of the Australian economy, right? So for these systematic risk, it cannot be diversified away, so it stays the same regardless of the number of securities in the portfolio. Also, the diagram shows us that at around 25 to 30% 30 securities in the portfolio, all of the unsystematic risk is eliminated, meaning that from about 25 assets onwards, the diversification benefits becomes really small. The systematic risk of a security or a portfolio depends on its sensitivity to the effects of market-wide factors, right? So again, as we can see, the systematic risk component doesn't change regardless of how many securities we hold, if all the securities are exposed to the same market-wide factors. The relationship between unsystematic risk and systematic risk is very important. So in asset pricing models, because we assume that investors are able to diversify unsystematic risk, therefore from a asset pricing point of view, we don't expect investors to require additional risk premium for bearing unsystematic risk, right? So anything that can be diversified away easily should not be rewarded, right? So shares with different levels of unsystematic risk should not have different levels of returns in that sense. So the concept of diversification and systematic risk and unsystematic risk is very fundamental to financial asset pricing models. So stemming from the previous slide, when we argue that if investors can diversify unsystematic risk away easily, then the only relevant risk measure should be the systematic risk component, right? So therefore, for the individual assets, the relevant risk measure is the covariance between the individual assets and the market or the market-wide returns, right? So we mentioned that the systematic risk component is due to market-wide factors, and so to measure the systematic risk component of individual assets, we measure that using the sensitivity or the covariance between the asset returns and the market returns, right? To standardize our covariance measure, we can use a measure called beta. So beta is simply just the covariance between the individual assets and the market asset and the market returns, scaled by the market variance, right? So the only thing that is related to the individual asset here is the covariance between the asset and the market portfolio, right? So this beta measure therefore reflects the fact that only the contribution of the asset to the total market-wide variation matters in asset returns, right? So building on the concept of diversification, so if we consider all risky assets in the economy, if we have all the risky assets in the economy, there will be no limit to the number of portfolios that we can form, right? And the expected returns and standard deviation of the different portfolios can be calculated, right? So if we were to compute the expected returns and standard deviation for all the possible portfolios in the economy, we would then be able to construct a region like this, right? So the curve AB from here to here is what we call an efficient frontier, and this curve includes all the portfolios that are efficient in the sense that they maximize return at the same level of risk, or they minimize risk at a given level of returns, right? So this is the foundation theory for modern portfolio theory, and this is developed by Markowitz from the idea of diversification, right? So the theory says that for any given set of assets, there exists an efficient frontier, which is the combination of portfolios with the best returns given a certain level of risk, or the lowest risk given a certain level of returns, right? So if we look at the graph from before, we will see that this is the efficient frontier from point A to point B. We have also some portfolios that we can choose below this region, yeah? But we say that curve AB is the most efficient combination of portfolios, because for any point below this curve AB, we can always find a more efficient portfolio on curve AB, right? So any portfolio below the efficient frontier is therefore inferior, because we can always find something better along the efficient frontier, right? Investors also cannot construct a portfolio beyond the efficient frontier, given the current set of assets, right? So any point above curve AB is impossible, given the current set of investments that we have, right? So curve AB is therefore the maximum utility that we can get. The key assumptions under Markowitz theory or the portfolio theory is that investors are risk averse, and therefore they try to maximize returns at a given level of risk, right? So if we were to think about a risk averse investor, their utility curves look like this, yeah? So linking the portfolio theory and the expected utility theory, we will find that an investor with this utility curve would prefer to invest in this portfolio, where the utility curve meets the efficient frontier, right? This is when they maximize the utility. If they choose any point below this frontier, then their utility is not maximized, yeah? The second assumption here is returns follow a normal distribution, meaning that we can use the standard deviation of the distribution as the measure of risk, and returns can be measured using the mean, right? Using the mean of the distribution. Okay. So this assumption is fairly important in asset pricing models, because in the model, our objective or the objective of the agent is to minimize risk and maximize returns, yeah? If we have a non-normal distribution, then we have to worry about the other moments as well, namely the kurtosis of the distribution and the skewness of the distribution. But in a normal distribution, we only measure risk as the standard deviation of distribution, right? And then we try to minimize the standard deviation at a given level of risk, at a given level of return, or we try to maximize return at a given level of standard deviation, right? So to summarize the lecture, in this lecture we look at a very fundamental concept to asset pricing or portfolio investment, that is diversification. So we say that when we combine different assets with less than perfect correlation, the total portfolio risk can be reduced, because we eliminate the unsystematic risk component, right? As we see before, the value of diversification or the benefit of diversification changes according to the correlation of different assets, yeah? So when we have a lower correlation, we have more diversification benefits. the positive correlation that exists between returns on most risky assets impose a limit on the degree of risk reduction that can be achieved by diversification. So here we talk about systematic risk. Yeah. So if assets are correlated, that's because they are driven by the same common factors, and we can't eliminate those factors by diversification. We then distinguish systematic risk from unsystematic risk. So because of diversification, when we try to think about a relationship between risk and return, we only consider systematic risk, right? Because unsystematic risk can be diversified away, and therefore investors are not expected to be rewarded by bearing more unsystematic risk. We finally introduce Markowitz efficient frontier. So we argue that risk-averse investors will always try to hold portfolios along the efficient frontier, because that's when their utility is maximized. Yeah, so they get the highest return at a given level of risk, or they get the lower risk at the same level of return. So that concludes part 2 of module 3.